pick it up afterwards. Okay, let's go ahead and get started. So today I wanted to finish up our discussion of cosmology. So let me remind you of our basic starting point for the theory of cosmology, which is the FRW equation, which is the equation which allowed us to determine how rapidly the universe is expanding if we know the amount of energy density present in the universe. So that, for example, r dot over r squared, the logarithmic time derivative of the radius of the universe squared, is equal to Newton's constant times some numerical factor times the total energy density present in the universe, which it's convenient to write as a sum of all possible different kinds of matter that is present in the universe. So, for example, you have an energy density due to vacuum energy, an energy density due to curvature, an energy density due to normal matter, which is often referred to as dust, and an energy density due to radiation. And in order to understand the basic history of the evolution of our universe, we just need to understand that as the universe expands in size, as r increases, these various different terms here appearing on the right-hand side of the FRW equation behave differently as a function of r. So vacuum energy is the energy density of empty space, meaning that it doesn't change as a function of r. As the universe grows bigger, the amount of energy contained in vacuum energy grows bigger as well. It grows like the volume of space, and so rho vacuum is unchanged as a function of r. Whereas the other types of energy that appear in our universe do dilute as the universe expands. So rho curvature behaves like 1 over r squared, and rho dust behaves like 1 over r cubed. That 1 over r cubed just coming because as the universe expands in size by some amount, the density of matter must decrease as that matter is spread out more thinly across the entire universe. And rho radiation was the term that redshifts, i.e. decreases in energy, the most rapidly as a function of r. So whereas rho dust went like 1 over r cubed, rho vacuum was independent of r, rho radiation falls off like 1 over r to the fourth, because not only does radiation get diluted as the universe expands, it also redshifts in frequency, and so it loses energy. And so if one rescales this equation a little bit by defining omega vacuum to be 8 pi g rho vacuum over h squared, and likewise defining omega curvature, omega dust, and omega radiation similarly, then these different omegas are simply the dimensionless quantities that are associated with the density of these different sorts of matter. And the FRW equation is just the statement that their sum has to be equal to 0. Or, sorry, has to be equal to 1. And the relative values of these omegas tells you at the point in time that you're studying which one of these different types of matter is dominating the evolution of the universe. So today, omega radiation and omega curvature are very small. They're experimentally indistinguishable from 0, which is not to say they're necessarily exactly 0. For example, I believe omega radiation is known to be about 0.1% or something like that today. Omega vacuum is about 0.75, meaning that 75% of the energy in the universe is contained in this mysterious vacuum energy, sometimes referred to as dark energy. And the energy density of normal matter is about 0.25. So it makes up about 25% of the matter content of the universe. And this normal matter falls into two parts. So there's the usual stuff, by which I mean stars, galaxies, planets, and so forth. And then there's so-called dark matter. And currently, the best models of dark matter are as a bath of fundamental particles which interact very weakly with all of the normal matter that we see around us. So that, for example, in this model of dark matter, we're currently being bombarded by dark matter particles as we speak, but because they interact so weakly with normal matter, we actually don't perceive them except in a very, very indirect way by studying their gravitational influence on the motion of stars as they move around the galaxy. So, for example, the density of dark matter particles traveling through this room right now is very, very small, and they interact very weakly, so they're difficult to observe. But they're spread throughout our galaxy homogeneously, and there's so much space in our galaxy that even though their density is very low, there's enough of them that they have an important gravitational influence on the dynamics of our galaxy. As, for example, you're going to investigate on one of the problems you'll do for Wednesday. Questions?
Does that mean they also interact with each other?
They do interact with each other weakly. Well, nobody's entirely sure, but that is what is believed, yes. So yes. So they don't clump up very well. That is one of their known properties. So all we know about these supposed dark matter properties are things that we can infer indirectly. For example, we know that they have a certain mass. We know that they contribute a certain energy density to the evolution of the universe and to the dynamics of galaxies. We can indirectly understand various constraints on their properties using our models of cosmology, which I'll actually describe in a few minutes. But we know very little about them directly. And I think there's a reasonable chance that within your lifetime as physicists, even within the next 5 or 10 years, you'll see newspaper articles and journal articles where the nature of dark matter is really nailed down specifically. I should mention that there are a number of different competing models for dark matter. So the model that I'm referring to here, where they're weakly interacting particles, is known as the WIMP model of dark matter. So dark matters are WIMPs, weakly interacting massive particles. The competing model for dark matter, which I think has only recently fallen out of favor, is the so-called MACHO model. MACHO stands for Massive Compact Halo Objects. Okay, clearly they chose that that name for semantic reasons. But what is a MACHO? MACHOs are just normal stuff, mass objects whose mass is large, but not so large that they would be dense enough to undergo fusion to create a star. So, for example, a bunch of planet-sized objects like Jupiter or Saturn just hanging out around the galaxy, which are very massive, but not so massive that they would collapse, that the pressures inside them would cause the hydrogen in them to undergo nuclear fusion, so they wouldn't ignite to form stars, but instead they would just contribute indirectly to the evolution of galaxies through their gravitational interactions. Actually, there have been many, so we discussed gravitational lensing previously in this class. Gravitational lensing is one of the primary ways that we would observe these machos, and they have not been so observed, which is one of a number of reasons why I think that the WIMP model of dark matter is the one that's currently most favored. But it's still a very much an open subject. Okay. So let me comment briefly on the future of our universe. Okay. So because omega lambda, sorry, I called it omega vacuum, is positive, that means that our universe will expand forever at an exponential rate. So at an exponentially increasing rate. In particular, at very late times, when the size of the universe is very large, all of the other terms which appear up here on the right-hand side of the FRW equation become very small, and H, which was R dot over R, will approach a constant, so that R will grow exponentially in time. So in particular, that means that R dot, which is H times e to the ht, grows exponentially in time. Now, at this point, people are sometimes confused by statements like this because we have learned in special relativity that nothing can travel faster than the speed of light. But r dot is a velocity. In particular, according to the Hubble relation, it is the velocity with which some distant galaxy is going to be receding away from us. And you can see that if it grows exponentially in time, then in not too long, it's going to be going faster than the speed of light. And the point to keep in mind is that the basic principle of relativity states that nothing can travel faster than the speed of light with respect to space-time, but space-time itself can move faster than the speed of light. And indeed, we see that if vacuum energy is non-zero, then at late times, in the very far future, our universe will be expanding at speeds that are growing exponentially in time. And in particular, will be expanding faster than the speed of light. And if you think about what this means for the future of our universe, this is really the ultimate existential nightmare. Okay. Why is that? Well, it means that eventually, every 2 points in this universe will be receding away from each other faster than the speed of light. And so that if we were to wait here in our Milky Way galaxy, looking out at the night sky for another 100 billion years, eventually all of the other galaxies, so all other galaxies, will eventually be receding away from us faster than the speed of light. So in particular, they will be causally inaccessible. What does that mean? That means that if you have a friend in the Andromeda galaxy, well, you better have any conversations you want to have with them right now. because eventually they're going to be receding away from us faster than the speed of light. Any signal that you send them will never reach them because that signal will be traveling only at the speed of light. And likewise, that signal will be traveling towards us at the speed of light, and we will be receding away from our friends in the Andromeda galaxy at a speed greater than the speed of light, and so their messages will never reach us. And this is yet another manifestation of an event horizon, which is something that we have already encountered twice in this class, once in the context of an accelerating observer, and again in the context of black holes. And you can see here that event horizons are not merely of theoretical interest. Eventually, they will be of experimental interest as well, because we will indeed observe them. And right now, we are not in a phase of the evolution of the universe where the universe is expanding exponentially rapidly. Why is that? Well, remember that omega vacuum is about 0.75, and omega normal matter is about 0.25. In a phase where we're expanding very, very rapidly, exponentially rapidly, omega vacuum would be very close to 1, and everything else would be very close to 0. Okay? So it'll take a little bit more time before we enter this exponentially expanding phase. It might take another 100 billion years or so, which is not a long time in terms of the history of the universe, as far as we think. It does mean, however, that if your friends are in the Andromeda galaxy a million light years away, you could have a very long conversation with them. You could send signals back and forth, a few thousand times, a few 100,000 times, maybe a million times, before eventually they will be completely inaccessible due to the expansion of the universe. I should mention, however, that whereas the other galaxies will be receding away from us at speeds exceeding than the speed of light, everything within our own galaxy is gravitationally bound together. Okay? And this approximation, remember, the model that we developed for the expansion of the universe assumed that everything was completely inhomogeneous. Everything was completely homogeneously distributed. So if you want to study the evolution of stuff inside our galaxy, for example, then you need to remember that that FRW model is not quite right. And so it turns out that even though the other galaxies will be receding away from us exponentially rapidly, everything within our own galaxy is going to be bound together for the rest of the history of the universe. So it's just like No Exit, that Sartre play, where hell is being trapped in a room with your friends forever. There's a question here.
So are there some points in the universe right now that are far enough away that if they send a signal to us, by the time it gets close to us, we'll be traveling away faster than the speed of light?
That's an excellent question. So the question is, are there things right now which are outside of our event horizon? Okay. And the answer is probably. Okay, but if there were, the answer is that according to this model, there's no reason to think that there aren't points outside of our current event horizon. But we would have no way of knowing it, right? Because by definition, something outside of our event horizon is something that we'll never meet, something that we'll never see. So in most of the models of cosmology that we believe, there's a very, very great deal of space that is outside of our current event horizon, but that's something that we'll never be able to verify experimentally. So any model like that, you would have to assume some strong version of the Copernican principle in order to say that, which is the assumption that everywhere else in the universe, the physics looks identical to our universe. There's a question over here.
Is there any chance that this time the value of C itself will change?
Okay, good. I should say that the story that I'm telling now assumes that vacuum energy really is something that does not dilute as a function of time. Okay. As I mentioned last time, there are other models where that is not the case. I think none of them are considered particularly likely, but that there are models where that is the case. Another question.
So the universe being 45 billion light years.
Yes, good. Good. So when we say the universe is 45 billion light years across, what we mean is the currently observable universe.
So it could be much bigger.
could be much bigger. Could certainly be much bigger. Yes, good question. Yeah.
Is there a point if there's an infinite expansion, I guess at one point the stretching of the space will overcome even the irregularities?
That's right. So let's get, that's actually, that's something that I will mention in a minute. Okay, that's actually something related to something that I'll be mentioning in just a minute. Okay. Okay. So that's the future of our universe. What about the past? Okay. So at early times, other forms of matter dominate. So for example, right now, vacuum energy and normal matter are the two sorts of matter that appear to dominate the evolution of our universe. But remember that the energy density of radiation falls off like 1 over r to the 4th, whereas matter falls off like 1 over r cubed. Thus, at very small values of the radius, the energy density in radiation vastly exceeded that in all other forms of matter. So one can see that intuitively just by noting that as the universe becomes smaller and smaller and smaller, you have more energy compacted into a small region. And so the universe will be some very hot, dense sort of plasma. And the universe began as some very hot, dense plasma. And as the universe expanded and cooled, there were various different phase transitions. That is to say, there were various different phases of matter which dominated the dynamics. That is to say, which dominated the energy density of the universe. So just as if you take water and you cool it down, it will undergo transitions first from a gas into a liquid, and then from a liquid into a solid. The universe, as it cooled down, underwent various sorts of phase transitions, where the matter that started out as some hot, dense plasma would undergo some transition into different types of matter. And these different, and so it turns out that in studying the history of the very early universe, we also need to understand very well the structure of matter when it's very, very hot, when it's very, very dense. And so indeed, this is where particle physics and nuclear physics meet with cosmology in our description of the universe at very early times. So if you want to just understand a brief sketch of the history of the universe at early times, so the smallest constituents of matter that we know of are quarks and gluons. Okay. These are the particles that make up protons, neutrons, and so forth. And at very, very early times, the universe was very hot and very dense, and it was a soup of quarks and gluons that were all running around and banging into each other. And then, as the universe cooled, these quarks all bound together into protons and neutrons, i.e. into nucleons. So a nucleon is just the fancy name that we give to something which is either a proton or a neutron. And then, as the universe cooled further, the various protons, neutrons, and electrons, which were making up the soup of the universe, eventually bound together to form atoms and molecules. And it is this final phase that is the one that we live in, the one where the universe has cooled sufficiently that the soup of protons, neutrons, and electrons have all bound to form atoms. And indeed, they bound to form atoms a very, very long time ago. Okay. So in the study of cosmology, we typically give special names to these transitions. So we call this the confinement transition. Okay. So previously, quarks and gluons were free to propagate around. But after this transition, the quarks were confined together to form protons and neutrons. And this transition we call recombination. I don't know what the re means in recombination, but certainly you can think about protons, neutrons, and electrons combining together to form atoms. And this phase where the universe is dominated by nucleons, protons, neutrons, and also electrons, is given a special name. We call this Big Bang nucleosynthesis. So when people talk about the Big Bang, this is the model that they're talking about. And indeed, much of what we know about the theory of nuclear matter actually comes from our study of this phase of the universe known as Big Bang nucleosynthesis. So, for example, by studying this soup of particles that made up the Big Bang nucleosynthesis phase, we can predict the relative abundances of elements that were created at early times during the expansion of the universe. For example, after the universe emerged from this Big Bang nucleosynthesis phase, the various nucleons combined with electrons into atoms, and we would be interested in understanding what sort of atoms were created. And it turns out that roughly 3/4 of the matter in the universe formed hydrogen, roughly 1/4 formed helium, 1 or 2% lithium, and so on and so forth down the periodic table. And it is through our understanding of nuclear physics, combined with our model of cosmology, that we are able to understand so precisely how these various elements were created at early times. Of course, other elements are created during the evolution of our universe at later times through the fusion processes that take place in stars. But it turns out that this understanding of the creation of nuclei during the Big Bang is one of the strongest constraints that we have on our understanding of nuclear and particle physics. Question? I'll get to that in just a second. So one other point that I should make is that before recombination, the universe was a soup of charged particles. If you have protons and electrons that are freely propagating, they're banging around all over the place, then this soup of charged particles means that photons will not propagate for long distances. Why is that? Well, if you have a bunch of protons and neutrons and electrons, the protons and electrons of which carry charge, then a photon won't be able to go very far before it bangs into one of these charged particles. Remember, photons are electromagnetic waves. What does electromagnetism do for a living? Well, it interacts with charged particles. After recombination, when all of the protons and electrons have bound together to form atoms, these atoms are electrically neutral. You have the same number of electrons as you do protons. And so that means that these photons will be able to propagate. So there were always photons in the universe. But before recombination, the universe was opaque in the sense that it was very hard for light to propagate long distances. So this recombination time is also the time when the universe goes from opaque to transparent. So the recombination is as far back as we can see using light. So in particular, if you lie on your back and you look up at the night sky, then as you look at very distant objects, you're also looking backwards in time. But you'll never see farther back in time than the time of recombination, because before that, light couldn't propagate very well. And so if you see far enough back in time, eventually you'll hit a surface beyond which you can't see. And this is known as the cosmic microwave background surface. Or the CMB surface. Sorry, I can't spell surface correctly. So in particular, the echoes of this recombination transition are what is visible to us in the cosmic microwave background. And the surface from which all of this radiation is being emitted is known as the cosmic microwave background surface. So indeed, some of the most interesting and exciting experiments that are being run right now are satellite experiments that give very, very detailed measurements of the cosmic microwave background by studying exactly the energy and spectrum of the various photons that are being emitted by this cosmic microwave background. Indeed, I think the cosmic microwave background may have actually been discovered by accident because it turns out that it's very annoying for people trying to do delicate radio experiments. Indeed, actually, some fraction, if you turn on a TV set and you, okay, I'm going to use some very old-fashioned terminology. A TV set is an ancient device that was used to communicate via electromagnetic radiation. And there used to be a thing called a tuner, okay, a dial that you turned to go between different channels. And if you go between two channels on a tuner, you'll just see white noise. You'll see, just a bunch of static. Okay. And I think that some finite fraction of I think it's like 10% of that static actually comes from the cosmic microwave background. It's something that is indeed very observable. And a lot of what we know about cosmology, actually, over the last from the last decade or so, comes from detailed observations of the cosmic microwave background. So let me just plug in just tell you a few numbers. Okay. So frequently, when we talk about distance in astronomy and cosmology, it's frequently common to talk about distances not in terms of kilometers or megaparsecs, but rather to use directly Hubble's law and measure distances in terms of redshift factors. So, for example, if you have an object which emits radiation or emits a photon at a given frequency, then there will be some redshift factor, the ratio of the frequency of the emitted photon to that of the observed photon, which will be bigger than 1. So we typically call it 1 plus z, where z is a number referred to as the redshift of the object. So z is bigger than 0. And this factor 1 plus z is nothing more or nothing less than the radius of the universe now divided by the radius of the universe when the photon was emitted. And this is true for FRW, for the FRW universe. This is just the statement that if you increase the size of the universe by some factor, then if you have a photon, which is, say, some standing electromagnetic wave, when you increase the wavelength, when you increase the size of the universe by some factor, you also increase the wavelength by the factor, and so you decrease the frequency by that same factor. And so Hubble's law, for example, for nearby objects, Hubble's law tells us that z is essentially or approximately the velocity as measured in units of the speed of light. Okay. Remember, the non-relativistic Doppler formula says that F emitted over F observed is 1 plus V over C. So for nearby objects where we can trust the Hubble law, where the Hubble constant, or the Hubble parameter really is approximately constant, Z is really essentially V over C. But of course, for more distant objects, you need to correct this by taking into account the fact that H and R are changing in time in some complicated way. So when we talk about objects that we see in the night sky, very distant objects, such as galaxies and quasars, are typically referred to as high redshift, very, very far away, if z is greater than or equal about 0.1. So a very distant galaxy that one might observe will have a redshift of about 0.1, so it'll be receding away from us at velocities that are about 1/10 the speed of light. And indeed, one can, oops, something happened there. Uh-oh. Good, thank you. Indeed, the most distant object that one has observed is a quasar, which has a redshift of about 8.6. Okay. Every year when I teach this class, I really have to go on the Wikipedia page and make sure that it hasn't changed, because this is one of those forefronts of astronomy that really is being pushed very rapidly. So this is the highest redshift object that has been observed. You can see this is clearly a case where you shouldn't use the naive Hubble law that V over C is proportional to Z. Otherwise, you would say that this thing is receding away from us at 8.6 times the speed of light. You really need to take into account the fact that the Hubble parameter is decreasing in time, and that one needs to account for the expansion of space in a slightly more sophisticated way. And the cosmic microwave background, that is to say, the last surface, which we can see using photons, is at a redshift of a few thousand. Okay. So it's of order 10 to the 3. And the temperature of the CMB, the temperature of this radiation, is about 3 degrees Kelvin. So it's very cold. but not unreasonably so compared to other sorts of physics experiments that we can understand. In fact, when the cosmic microwave background was observed, it was very quickly realized that this led to a puzzle in our understanding of the evolution of the universe. So in particular, the cosmic microwave background has or exhibits what is known as the horizon problem. So what is the horizon problem? So if you lie on your back and you look up at the cosmic microwave background, then you see many different regions of the universe. And in fact, in the standard Big Bang model, so in the standard cosmological model, the regions of the CMB, which we are now observing, were not in causal contact until very recently. So in particular, if this is a picture of the night sky, okay, so there's the night sky, then when you look up and measure the CMB, there are all of these different little regions, little patches of the night sky. In fact, they're of order 10 to the 5 of them, all of which should have been outside of causal contact with one another up until very recently. And because they are out of causal contact, one expects large fluctuations in the temperature of these regions. So in particular, if you think about the behavior of the early universe, then we saw that the cosmic microwave background temperature was about 3 Kelvin. Okay, so it's very cold. But if you have some material that is at some temperature, then in order for that material to all be at the same temperature, that material has to have been in contact with different parts of the material for a long enough time to come into equilibrium. Okay. If you have two different materials that are at different temperature, and you bring them close together, eventually they'll come into thermal equilibrium and they'll be at the same temperature. And the horizon problem is the problem that when we actually observe the cosmic microwave background, you see different parts of the universe which weren't in contact with another for a very long time, and so you would expect them to have fluctuations in their temperature that reflect the fact that they haven't come into thermal equilibrium. However, as was very quickly observed after the discovery of the cosmic microwave background, the variations in the temperature among these different 10 to the 5 regions in the cosmic microwave background has a delta T over T, the variation of the temperature divided by the temperature, that is not of order 1, as you would expect, but is in fact of order 10 to the minus 5. Okay. So it's 5 orders of magnitude too small to be accounted for by our current model of cosmology. So what does that mean? That means that these regions must have been in contact with another. And in particular, that implies that the early universe must have been smaller and expanded more rapidly than we first thought. And so the proposed solution to this problem is what is known as the theory of cosmological inflation, which is that the universe underwent a period of exponential expansion at very early times. Sorry, I meant to say exponential expansion. Of course, the universe always, we know, underwent some sort of expansion. But the theory of inflation is the theory proposing that the universe underwent exponential expansion at early times. Question?
So when exponential and then back.
That's correct. That's correct. Okay. Okay, good. So the question is, what sort of, how could it do that? We saw that an exponential expansion in the usual FRW equations is something that happens at very late times, okay, when everything else has redshifted away, all of the matter has diluted. So how is it possible to have an exponential expansion at early times? In order for that to occur, there must be a new sort of matter responsible for that evolution at early times. Okay. And people give a name to that type of matter. They call it the inflaton, because it's the thing that made the universe want to inflate. Okay. Just like a photon is something that makes the universe want to float. So people invented this new sort of matter. This matter has never been, so the prediction is that there's a new type of particle, or if you want to think about it, this inflaton is conjectured to be a sort of fluid that filled the universe at very early times and made it want to expand exponentially. And right now, the only evidence that we have for inflation comes from cosmology. Okay, we have not built any particle accelerator which has been able to see this inflaton. It would have to be a very large particle accelerator, much larger than the one running at the much larger than the one running at CERN right now. But the evidence for inflation is really quite compelling. Not only does it explain the horizon problem, but it makes very, very specific predictions for the size and nature of the fluctuations in the cosmic microwave background. These predictions were understood quite well in the 80s and 90s, and then the recent generation of satellite experiments has confirmed them with remarkable accuracy. Okay. So they predict not just, for example, the size, this 10 to the minus 5, but the behavior of these fluctuations as a function, for example, of their frequency, things like that. So I think the jury is still a little bit out on inflation, but the smart money is that inflation is correct. Okay. And I think that, I bet you'll see a Nobel Prize for it within the next 10 years or something like that. There were a couple questions. Maybe you were first.
Going back just a little bit, I'm not sure I understand how regions can be out of causal, be causally separated and then come back after.
Yeah, okay. So what do we mean? Well, let's put it this way. When you lie on your back and you look up at the night sky, you can look in lots of different directions. You can see that direction, that patch of the night sky over there, and that patch of the night sky over there. They're very, very far away from one another. Okay. And so the question is, so right now, of course, it's possible, for them to be sending light rays back and forth, for them to be in causal contact with one another. But the question is, given our model for the evolution of the universe, how long were they in causal contact? Were they in causal contact for the whole history of the universe? In which case, maybe they would have enough time to come into equilibrium with one another. Or are they not? And did they not have enough time? And so that's sort of the salient question. Yeah, I'm not sure if I answered your question. Maybe I'll answer some other questions, and then you can decide if you want to ask again. Okay, I think these guys were next. Yeah.
This might not be a meaningful question because it might not have a meaningful answer. But instead of conjecturing that this inflaton is there making the universe inflate, how do we know the rules just didn't work differently back then in the first few milliseconds of the universe? After all, we know that the universe isn't isotropic with respect to time.
Let's put it this way. Yeah, I mean, the question is really why the inflaton and why not something else? Okay, one is always free to postulate various modifications of physics at early time. Indeed, the inflaton is one conjectured modification of physics at early times. Okay, you then have to come up with a quantitative model for that modification of physics. The inflaton is a certain type of particle that we very rarely see, that we don't actually see around us in nature. It has very similar properties to what's known as the Higgs particle. Okay? And so I think one of the reasons why people came up with the model of inflation is that it was very, very similar to models of physics that appear to be correct in the standard model of particle physics. And at the end of the day, one is free to come up with various different sorts of models. There are various constraints that these models have to satisfy, which turn out to be very, very difficult to satisfy. And the inflationary model is the one that appears completely self-consistent, that satisfies all of the constraints that we know, and it has been experimentally verified, at least to some extent. There's another question, and then you. Yeah.
It's kind of related to what you just said. I was going to ask, so did you create like a new gap in the standard model?
So the standard model is, for example, this particle is something that is vastly more energetic than the sort of particles that we describe in the standard model. So it's not so much a gap in the standard model as it is a description of the dynamics of the universe when it was very, very hot and dense, so much more so that we have no idea what particle physics looked like. Okay. If you want to, you should really ask, what would happen if you tried to take this diagram backwards in time? Okay. And the point is that we have no freaking idea. Okay. Because the standard model of particle physics only goes this far. Okay. It doesn't go any farther back. And so we just don't know what happened. The standard model makes no predictions there. Okay. And so based on these indirect arguments, we predict that there's another sort of particle, an inflaton. Maybe there were other phase transitions between the inflationary phase and the quark-gluon plasma phase. It seems likely. I mean, there's about 10 orders of magnitude of energy difference or temperatures there. So it seems probable. But we don't have very many tools for studying it. One last question, and then we'll have to stop. Yes?
So the predictions made around this inflaton particle, you said it's similar to the Higgs and it's much more energetic. Is there any other differences between the Higgs and
Yeah, absolutely. Absolutely. There's many.
Prediction,
Yeah. So the Higgs has very specific properties. The inflaton, we really don't know very much about the inflaton. Okay. Cosmologists there are cosmologists who've devoted their careers with coming up for different models for the inflaton and understanding its implications. This is cutting edge stuff. I mean, I suspect that, some finite fraction of things that I've told you today will turn out to be wrong. Okay. Because that's what happens when you talk about physics that's being done today. I've told you our best understanding, but I could always be wrong. Okay, but next class